Welcome back. Today we're going to talk all about asymptotes, which is a term that you probably have heard from pre-calculus. And now we've got a new tool to help us out with figuring out whether or not asymptotes exist. And that tool is the limit. And the limit will help us as part of our definition of what an asymptote is. Sorry about the face cam. I wasn't able to get it to work, but you can see my face over here off to the right. So we got a few examples, but they're actually relatively quick examples as we go through of all of our different types of asymptotes. So let me lead you first through a definition. Both of our limit types involving infinity are connected greatly with the idea of the asymptote. So we could have either what we call a limit at infinity, where we're going to either positive or negative infinity with our limit, or we can have an infinite limit. In that case, the answer for the limit is either infinity or negative infinity. So the word asymptote is a little misleading. A lot of people mistakenly believe that you can't cross a horizontal asymptote. And in fact, the word asymptote comes from the ancient Greek for non-intersecting. But as a matter of fact, you actually can cross a horizontal asymptote. Vertical asymptotes are a different issue, as we'll see. But a horizontal asymptote really is just what your end behavior is of the function. And you can do all kinds of things with the end behavior of a function. So some definitions here. As the outputs become unbounded, all right, as our outputs become unbounded, we get what we call a vertical asymptote with an equation of x is equal to a. So you probably have heard that terminology before. In other words, f of x approaches infinity or f of x approaches negative infinity as x either approaches a from the left or the right. This is what we call an infinite limit where our outputs are unbounded. We also can get what we call a horizontal asymptote if the inputs are becoming unbounded. What we call this a limit at infinity. And here we would get a horizontal asymptote of y is equal to L. So what does that mean? Well, we're going to investigate limit as x goes to infinity of f of x and limit as x goes to negative infinity of f of x. And we might get a value L for either one of those. That means, by the way, it's possible for you to get two different horizontal asymptotes, as we'll see. And the reason for that is because we're dealing with two limits, both the limit as x goes to infinity and as x goes to negative infinity. It's like end behavior. You have two descriptions you need to make of your end behavior, both as you go to the left side of the graph and the right side of the graph. Some basic rules for finding asymptotes. If a more powerful function is on the bottom, and we'll discuss what that means in a second, the horizontal asymptote is y is equal to 0. However, if the more powerful function is on the top, there is no horizontal asymptote. In special cases, we might get what's called a slant asymptote, which is not horizontal. And if the function types balance, then we get what's called a horizontal asymptote, where we compare our leading coefficients. It's going to be some particular numerical value other than 0, as we'll see. In order to help us out with this, we need to figure out what a more powerful function is. And for now, we've got a little bit of a pecking order with some nicknames to help us out here. All right. So the most powerful function that we can think of, the one that grows the fastest, is what we might call the power tower. Something like x to the x to the x to the x. As you know, there's a Chuck Norris sort of character out there, right, who's powerful more than you could even imagine. We also have x to the x. This is what I'm going to call the Jedi. Of course, there's no pictures of Jedis, or are there? I don't know. Maybe I just didn't include one. All right. That's going to be semi-powerful. Our next function on the list is what we call exponentials. Those I'm going to nickname ninjas. You can see them off to the side. Ninjas, they're kind of powerful. They're right in the middle of this. Those are functions like 3 to the x or 2 to the x. And by the way, 3 to the x is going to be more powerful than 2 to the x because we're going to call 3 to the x a third degree ninja. 2 to the x is a second degree. So imagine like a black belt or all the different belts that you might see in martial arts. And the third degree has reached a higher belt than the second degree. Okay, so this might, wait, what's going on? What's he talking about? We're going to see this in just a minute. So just kind of bear with me here. We also have what we call polynomials, all right? They're not quite as powerful as exponentials. That's why a lot of times people say something grows exponentially. They mean it grows a lot. Polynomials grow, but they don't grow quite as much. And they're not as powerful as the ninjas. So we're going to call those the pirates. And you can see the nice little pirate over here. So just like with the ninjas, an x cubed as a third degree pirate is more powerful than x squared, which is a second degree pirate. Okay. Then kind of lower on the list, we got our lumberjack. are logarithms. They don't grow very fast, but they still grow, with a great amount of speed, just not as fast as compared with the pirates and the ninjas. And then, of course, you got sine and cosine function. Those are the Tar Heel fans. They go up and down no matter how their season's going. Okay, but they're not powerful at all. All right, so let's do some examples, and I'm going to show you how this power tower works in just a minute. But as we go forward, let's make sure we understand what the meaning of our terms is. So what does limit as x goes to infinity of f of x equals -2 and limit as x goes to negative infinity of f of x equals 2 mean in terms of asymptotes? All right, this means that the function has horizontal asymptotes of y equals -2 and y equals 2 because we're looking at limits at infinity. On the other hand, what does limit as x goes to 3 from the left of f of x equal to infinity, limit as x goes to 3 from the right of f of x equals infinity mean in terms of our asymptotes? All right, and so when we see the answer as one type of infinity, either negative or positive, that means we have a vertical asymptote at x is equal to 3. And in fact, I've given two different reasons for that. All right, both the left side and the right side limit. All right, so the vertical asymptote example, suppose that f of x is equal to x squared minus 16x plus 55 over x squared minus 13x plus 40. Sorry, my face cam is off to the left here. Oops. All right, so let's find vertical asymptotes for this function. Well, first thing you might want to do is consider factoring. And once we factor, we notice that there's a hole in the graph at x is equal to 5. That's what we've been talking about all along with limits that we can actually find a numerical value for. We were able to cancel out the x minus 5 factors in the numerator. We still got a problem in the denominator though, and that's at the x minus 8 factor. So what we want to think about is for values that are a little bit bigger than 8, what's going on with this function? Well, if I plug in a number really close to 8, in my numerator I'm going to get a -3, a number close to -3, and a number close to 3. 8 minus 5 is 3, 8 minus 11 is -3. On the bottom, I'm going to get a number close to 0, but positive, and I get 3, a number close to 3. Right? So what we need to think about is when we're dividing by a number that's really, really close to 0, all right, we're going to approach some sort of infinity. And what we need to do is we need to look at what's going on with our signs. And in this case, we've got one negative sign. So since we're multiplying or dividing with one negative, we end up with one negative altogether, an odd number of negatives. And so we would say, since we're dividing by 0 and get a negative number, limit as x goes to 8 from the right of f of x equals negative infinity. And we can do a similar argument to show the limit as x goes to 8 from the left of f of x is positive infinity. And this limit right here tells us that our function has a vertical asymptote of x is equal to 8 because we get infinity or negative infinity as our answer for one of the limits. Okay, a couple of examples of how to look at limits at infinity. So I give you 3 examples right here. We've got, first of all, the limit as x goes to infinity of 5x plus 8 over 4x plus 8 with a lot of other terms that we don't even know. And we're going to assume that the x plus x to the 8 is our highest power here. So when we have the highest power, in order to figure out what our limit is, all right, one of the ways you would go about doing that is to divide your numerator and your denominator by whatever that highest power is. So in this case, we divide by x to the 8th. And when I do that, I notice that everything else just disappears and I'm just left with a 5 over 4. So basically the idea is if you have the same powers in your numerator and your denominator, your highest powers, I should say, your degree, all right, then you end up with a limit of the ratio of the leading coefficients. In this case, that's the 5 and the 4. If on the other hand, I've got something like 6x to the 8 and other smaller terms in my numerator, and 2x cubed and other smaller terms in my denominator, all right, when we compare the two, we're going to go through and we're going to divide by x cubed, all right? X cubed, when we divide by it, is going to end up making my denominator just 2. And when I divide by x cubed in my numerator, I'm going to get x to the 5th. I should say, I'm sorry, 2x cubed. So we get 1 in our denominator, and we get 3x to the 5th in our numerator. And then what we do is we realize, well, okay, as x goes to infinity, what's happening with this function? Well, this function goes to infinity. We get larger and larger y values when we plug in larger and larger x values. If, on the other hand, we look at the same limit as x goes to negative infinity, 6x to the 8th and 2x cubed, we get the same 3x to the 5th. But if we evaluate this as x goes to negative infinity, we're going to end up with negative infinity as our answer because we're raising a negative number large negative number to the 5th power. So we get a negative times a negative times a negative times a negative times a negative, which is also a negative. Right? So the end behavior of these polynomials will be helpful in helping us figure out our limits as we go to infinity. Now, here's another one to consider here. Limit as x goes to infinity of 7 minus x to the 4th over x cubed plus 2 to the x. So here is where our power tower comes into play. So in this case, we've got a 4th degree polynomial and a constant of 7, which doesn't contribute much, versus a 3rd degree polynomial and a 2nd degree exponential. So if you remember back on the power tower, the highest function that we deal with is the exponential, 2 to the x. So if we have an overpowering part in our denominator, we say the limit is equal to 0. Always look at the best fighter, even though the numerator is a strong pirate, it's a 4th degree pirate, it's no match for the denominator's ninja. The ninja wins, so since that ninja's in the denominator, we get 0 as our answer. Let's say we have limit as x goes to infinity of 2 times 7 to the x plus 5 over x to the 8th plus 3 times 7 to the x. So let's evaluate what's going on in this fight here. We've got 2 7th degree ninjas plus 5 neutrals, all right, over an 8th degree pirate and 3 7th degree ninjas. Well, who's actually going to fight in this battle? Well, we need to look at the ninjas on our top. The constants don't do anything. They just sit back and fight, or don't fight, I mean. They're just watching the action. So we got 2 7th degree ninjas, and then the 8th degree pirate really doesn't do anything in the fight against ninjas. All right, x to the 8 doesn't do much. So we compare the 2 7th degree ninjas to the 3 7th degree ninjas in the denominator. So when we compare, we get a ratio of the 2, and we get 2 divided by 3. So when confronted with the same, quote, degree in our numerator and denominator, we find the ratio of those coefficients. All right, so find the horizontal asymptotes for y equals 3 plus 2 e to the x divided by e to the x minus 5. Use limits to explain your answer. All right, so we look first at the limit as x goes to infinity. We take a look at our fight. We've got 3 constants. They're not going to fight much. And we've got 2 e degree ninjas, natural degree ninjas, over 1 natural degree ninja minus 5 constants. So what's really contributing to the fight? It's these 2 ninjas versus this 1 ninja. So the ratio is 2 to 1. So we say y equals 2 is a horizontal asymptote as we go to infinity. Now I forgot to tell you, the ninjas have limited powers. Ninjas lose a lot of their power and they can't travel backwards in time. Well, what do I mean? If we do limit as x goes to negative infinity, that's like going backwards in time. And what that means is, let's take the ninja 2 to the x. Limit as x goes to negative infinity of 2 to the x is the same as limit as x goes to infinity of 1 over 2 to the x, and that limit's 0. So if we go backwards in time, the ninjas disappear. They don't participate in the fight. So when you do that, all you're left is these constants in your numerator and your denominator that are going to fight each other. And so you end up with negative 3 over 5. So we get one horizontal asymptote of y equals 2 and one of y equals negative 3/5. Ninjas disappear as we go to negative infinity. All right, final last one. Find any horizontal asymptotes of h of x is equal to 3 times the absolute value of x minus 7 over x plus 8. So what we want to do is consider what happens to absolute value as you go to positive infinity and negative infinity. So absolute value as x goes to infinity is just the same as x, right? Absolute value of x is equal to x. So when you think of it that way, this function becomes 3x minus 7 over x plus 8. Now you compare, you got a first degree ninja, 3 of them on the top and 1 on the bottom, so that limit is 3, y equals 3 is a horizontal asymptote. If we go to negative infinity, this absolute value becomes negative x, so we get a negative 3x on the top. When we compare our ratio, we get negative 3, so y equals negative 3 is also a horizontal asymptote. Oftentimes, but certainly not always, as we'll see in class, square roots and absolute values produce 2 horizontal asymptotes because of the way that those functions operate. So in summary, vertical asymptotes involve infinite limits and horizontal asymptotes involve limits at infinity. And this power tower that we just talked about can be helpful for figuring out whether the function in the numerator or denominator dominates. And we'll get plenty of practice in class, and we'll see you on the next video.